If I'm trying to find all of the possible rational roots of this polynomial and then I wanted to actually verify which ones were roots, what I would do is I would think about P over Q. P, Q. P is always the constant. Q is always the leading coefficient. In this case, it's the imaginary one. So all of the factors of -2, 1 and 2, those are the only two numbers I can multiply together to get 2. All of the factors of 1 are 1. So if I were to continue on, I would have plus or minus 1 and plus or minus 2 as my only two possibilities. Those are my two possible rational roots. I took everything in the numerator, I divided it by everything in the denominator, and I simplified. But these are not my roots per se. So what I need to do is take them and figure out which ones are roots. I could do synthetic division, and if you look at a previous example, you'll be able to see what I did with the synthetic division. But I don't want to do it 4 times. I don't want to do it until I find which ones are actual roots. What I'm going to use is the remainder theorem mixed with the factor theorem, where I'm going to take what I think is a root and I'm going to substitute it in for x. If I get a remainder, if I get that it equals 0, then that means the remainder is 0, and if the remainder is 0, it's a factor. So I'm going to take 1. Actually, I want to change the color. Let's do purple. So I'm going to do f of 1. F of 1 is one cubed is 1. 1 squared is 1. Negative 21 times 1 is negative 21 minus 2. 9 times 1 is 1. So I end up with 1 plus 9. 1 plus 9 is 10. 10 minus 21 is negative 11. Negative 11 minus 2 is negative 13, which is not 0, which means that 1 is not a root. It is not a factor.